Hello and welcome to this clip going through the second question on the 2016 round 1 paper from the Chemistry Olympiad. So this is really just a few thoughts from me on how I might tackle this question. It's not a mark scheme. I've checked it against the mark scheme to make sure it broadly agrees with it, but it's not an actual official mark scheme. So let's start by having a look through the information it tells us. In the first paragraph, it talks a little bit about some uses of tungsten and also the fact that it has a maximum of a +6 oxidation state. So it tells us a little bit about its similarity in its behavior to sulfur. Even though it's a metal, it's a group, it's a D-block metal, tungsten. So transition elements often have some atypical behaviours that you might not expect of a normal classic metal that you would have learned about at GCSE. So it goes on to talk about tungsten 6 fluoride being used in the semiconductor industry and oxide of tungsten being used in electrochromic window. So electrochromic windows basically change colour when an electrical current or voltage, is applied. So when electrons are passed across them, they change colour. So they're used in airplanes. You can see from the picture that it's a photograph of airplane windows. So the obvious implication is if the sun is shining through an airplane window, it's going to be stronger sunlight because you're further up in the air. So therefore the idea of being able to control the colour of the window is quite useful to protect passengers. So then it says that tungsten occurs naturally in the tungstate ion, WO4 2-, which is analogous to sulfate. So a common tungsten mineral is scheelite, which is calcium tungstate, CaWO4. So the information we've been summarising in the top right-hand corner of the screen takes us down to the first part of the question. So it says draw a structure showing the bonding in the WO4 2- ion and give the OWO bond angle. So if tungsten is +6 oxidation state, there must be 6 electrons involved in the bonding. But if you look at the formula of the tungstate ion, it would suggest there's only 4 atoms bonded to tungsten. So that would mean in turn that there's at least one WO bond. So in its simplest displayed form, it would look like that because that's analogous to the sulfate ion. So obviously the reason that they told you that it was analogous to the sulfate ion is because many people would have seen the sulfate ion's displayed formula at A level. But the question actually wants you to give the OWO bond angle. So clearly, simply just writing it out the way I've done it is not sufficient. So if we remember that double bonds are considered as one bond pair, not 2 bond pairs, if we're using VSEPR theory of molecular shapes, that gives 4 bond pairs and no lone pairs around the central tungsten atom. So that gives us a tetrahedral ion and an OWO bond angle of 109.5. So although we've answered the question in the sense that we've given the bond angle, we haven't answered it yet in terms of giving it the structure, the shape. So what I suggest is doing it something like that, because that at least shows them that you're attempting to do a 3D diagram. I know it's probably quite difficult to visualize how you might use wedges and dotted lines if you have a double bond, but at least that gets a sense of what a tetrahedron looks like. Okay, so let's move on to part B. So the information it gives us is that treatment of scheelite with aqueous sodium carbonate gives a solution of sodium tungstate and a white insoluble salt. Okay, now it doesn't ask for state symbols, but let's just put them in to be on the safe side. So taking every single piece of information they've given us, I've just popped it in there, Usually I'd put the state symbols actually on the same line as the formulae, obviously, but I'm sure you can forgive me this small indiscretion at this point. So let's have a look at what we have to work out. The white insoluble salt means it's a solid. So what we need to have to do for part I is to give the equation of the reactant in scheelite and aqueous sodium carbonate. So it shouldn't be too difficult to work out by elimination that the only two things that haven't been put together are calcium and carbonate, because the sodium has been used up and the tungstate has been used up. And you should know from general knowledge at this point that calcium carbonate is not very soluble in water, so therefore it's likely to come out as a solid or a precipitate. So let's look at part II. So part II requires us to deduce from the information that's been given that hydrochloric acid and sodium tungstate solution produces tungstic acid. Now, it doesn't say anything else about the other product. Now, the sodium has to go somewhere. So you'd have to think about what sort of sodium compound you get. So they want you to give the equation for the reaction of aqueous sodium tungstate. So the way we can deduce this equation is that we know the tungstate ion has -2 charge, because two sodiums will combine with one tungstate, and one calcium will combine with one tungstate. So tungstic acid should have two hydrogen atoms because the tungstate ion will remain intact, just like the sulfate ion can end up as sulfuric acid, or the chloride ion can end up as hydrochloric acid. So hydrogen being +1 as an ion means that there's two of it that's required to balance the -2 charge of tungstic acid. So remembering the shape of the tungstate ion from before, tungstic acid obviously is going to be two H+. So what that means is that for those H+ to be released, initially there would have had to have been a covalent bond between the oxygens that are charged at this point and the hydrogen atoms that would have been present in the tungstic acid, as you can see from the equation at the top. So I'm trying as well to represent the nonlinear shape, the 104.5 degree bond angle across the tungsten oxygen hydrogen bond as well, because earlier I was making sure that I was trying to represent the tetrahedral shape, or 109.5 degree bond angle across OWO. Okay, so let's go on to part III. You probably just about have space to put it down at the bottom. So remembering that tungsten 6 oxide is going to be WO3, hence why it's tungsten 6. Oxygen is -2 oxidation states, so three of them needed to counteract and equal the +6 in tungsten. So this part of the question is asking for the formation of tungsten 6 oxide from tungstic acid. There's probably just about enough room to put it at the bottom of the screen. So just finding tungstic acid in the middle part of the screen is H2WO4 in aqueous solution, going to WO3 as a solid and H2O as a gas. And why do I say gas? Because if you look where the arrow is pointing, you can see that on heating, your tungstic acid gives tungsten 6 oxide. So the equation is now at the bottom of the screen with hydrogen as a gas. Water as a gas. Right, next bit is asking for the equation for the formation of tungsten metal. So there's probably not enough room to put that down at the very bottom of the screen on the right, so I'm going to pop it next to where the question is, sort of middle left of the screen. So it says that your tungsten 6 oxide can be reduced with hydrogen to give pure tungsten metal. So we're going to have WO3, we're going to have H2, and we're going to have W. So we need to put those together and think, what is the hydrogen removing? So the hydrogen is obviously removing oxygen, because that's all that can happen to turn tungsten 6 oxide into pure tungsten. There's no mention of heat this time round, so I'm going to leave it as 3H2O as a liquid. Why 3 moles of water? Because you need 3 oxygen atoms removed, therefore 3 water molecules, which in turn means 3 hydrogen molecules. So let's now go on to part C. So, here it talks about electrochromic windows, i.e. the photograph at the top that we mentioned a bit earlier. It says, a voltage is applied between a transparent layer of tungsten 6 oxide and a source of ions such as a lithium salt. You can probably just about make out that it's XLi plus X number of electrons to give you LiXWO3, or what they call tungsten bronze. So I've just reproduced the equation that they've put, so it's a little bit clearer on the screen. So you can see that a lithium plus ion has to accept an electron to become LiXWO3, because WO3 is not going to give the lithium ion the electron it needs to become a lithium atom. So the value of X is variable. It's given to you as an algebraic expression, because obviously different values of X give different colours. So therefore we want to be able to control what actual colour that the tint of the window changes to. So therefore what's going to happen is that the oxidation state of tungsten will vary depending on the value of X. So if we take X to equal 1, that means that that's the equation that we're working from. So in the final product, our LiWO3, we can assign +1 to lithium, and because there's 3 lots of -2, 3 oxygens, that gives a total of -6. This will give us an oxidation state for tungsten as +5 in this instance. But if you have X equals 0.3, this implies a charge of something that's not possible. You don't get a partial positive charge in the sense of a decimal. So +0.3 is not possible. It has to be a whole number charge, because you have to have whole numbers of electrons. You can't have 0.3 of an electron. So what we do is talk about the average oxidation state. So that's implying that possibly more than one oxidation state of lithium is at work here, which happens to average out at 0.3. So the oxygen stays the same, but it will still total -6. So the average charge of the lithium ions is +0.3, quote unquote. We can therefore use the oxidation state of the oxygen to arrive at +5.7 as the average oxidation state for tungsten. So moving down to the next part, you're being asked to calculate the densities of SF6 and WF6 relative to air. That is not the same as asking you to calculate the actual density. Now, actual density has its own equation for calculation. So density is mass over volume, and you are not given mass or volume at this particular point. So it gives you a little bit of information. It tells you that SF6 and WF6 are both gases at room temperature and pressure, WF6 being the most dense gas known under these conditions, and also the fact that it's extremely toxic because of what it produces when it reacts with water. So clearly, if you were to inhale it, it would react with water in your lungs to form 2 substances, and those 2 substances, they are going to be quite damaging. Otherwise, it wouldn't have been toxic. So how can we think about relative mass between the two? Because remember, mass is one of the functions of density, isn't it? So possibly relative molecular mass from the periodic table that will be provided, obviously, with this paper. So if we go down that route, we can work out the MR of SF6, and we can also work out the MR of nitrogen. So that gives us 146.06 grams per mole to the minus 1 for SF6 and 28.02 grams per mole to the minus 1 for N2. So the density relative to air, we're assuming that air being made up of nitrogen only is essentially the ratio between these two. So to get the relative density, we can take the relative mass, because mass and density are connected. So what that allows us to do is divide 146.06 by 28.02, which gives us, I believe it's 5.21. I'll just pop that into my calculator and see what I end up with. Okay, right. So the next part of part D asks you to do WF6 relative to air. So again, we're assuming that air is nitrogen only. So sticking with that idea, we do the same thing, but this time for WF6, which gives us a whopping 297.85 grams per mole to the minus 1. So this means that compared to 28.02, it's 10.63. So essentially, what this is saying is that the density of WF6 is over 10 times that of the density of nitrogen. Okay, moving on to part E, it says calculate the actual density of WF6 in grams per centimetre to the minus 3 at 298 K and standard pressure. So they're giving you some extra information. So you can assume that standard pressure means 100,000 pascals. So it shouldn't be too difficult to work out that this is going to be a PV equals nRT question, which we have done whether you're in the first year or the second year. I'm doing this particular clip at around January time, so usually most people have covered that in the first year by that point. So I'm not going to go through PV equals nRT in terms of its units. I'm going to assume that you know the units for PV, N and T. So what we need to think about is how can we sort of work in the information we've got into PV equals nRT. So let's make it easy on ourselves. Let's make moles 1. That makes N easy to eliminate. So if 1 mole of gas occupies 24,000 centimetres cubed, we know what 1 mole of WF6 will weigh. Mass is 297.83, I think. I'll come back to that in a sec. So PV equals RT if N equals PV over RT. Sorry, 297.85. So we can now work out the volume, because we need to get the volume. So V equals RT over P equals 8.314 over 298 over P. Sorry, I think I meant to say there 8.314 times 298 over P. So that gives us 2477.572 over 100,000. So that gives us 0.024777572 meters cubed. Remember, meters cubed being the unit that comes as volume out of PV equals nRT. But we want grams per centimetre cubed. So if we take 1,000,000 centimetres cubed being present in 1 metre cubed, so that means we've got 24775.72 centimetres cubed per mole to the minus 1. So what we've now got to do is work out density. So we now have the volume. So taking the density to be grams per mole to the minus 1 over centimetres cubed per mole to the minus 1, we can put the numbers in quite easily. So that gives us 297.85 over 24475.72, which leads to 0.0120 grams per centimetre to the minus 3. So the final part we have to do is to suggest an equation for the reaction of WF6 with water. So I'm going to put that down at the bottom. So remembering that there's 2 products that were produced, we now need to think about what those products might be. So it says that one of the products, it says that WF6 is an extremely toxic gas. And it says this is because its rapid reaction of water makes two substances. So the substance that I would go for is HF. Now it doesn't really matter which of the two equations at the bottom you use, because both would fit the bill. They're reacting WF6 gas with water. They're producing two products each, and in each case HF is made. I'm not putting in state symbols because there's nothing in part F to suggest that state symbols are required. But I'm going to stop at this point because the second part of the question, the second page of the question, gets quite big as well. So it's quite a big question. So in the interest of trying to keep the clip fairly short, it's 20 minutes already, I'd suggest perhaps that you go onto the Royal Society of Chemistry website and locate the 2016 Chemistry Olympiad paper. If you go into the Learn Chemistry section, I think that's where you'll find RSC papers and mark schemes. So for now, thank you very much for listening, and see you soon.